Hello everyone, thank you for being here. In this presentation, I will introduce our work in Visual Domain Adaptation Challenge 2020, and our method achieved top 3 performance on the leaderboard. This year, the Visual Domain Adaptation Challenge focused on the task of person re-identification, or person re-ID in short, which requires to retrieve images of a person of interest across multiple cameras from a gallery of photos. Unsupervised domain adaptation, or UDA in short, is proposed to adapt the model trained on the labeled source domain to the unlabeled target domain, where there are generally no shared identities between two domains in real-ID problems. The Visual Domain Adaptation Challenge introduced a synthetic to real benchmark, which is much challenging due to the fact that there are larger domain gaps between synthetic and real scenarios than those between two real scenarios. And the distribution of unlabeled target domain data is much more realistic than previous benchmarks. There are two main categories of existing works along the direction of UDA real-ID: domain translation-based and PseudoLabel-based. There are two main steps for domain translation-based methods. First, translate the source domain images to have the target domain style. Second, adapt the network to the target domain by training with source to target translated images. Domain translation-based methods are able to fully explore the potential of source domain images and their ground truth identities. PseudoLabel-based methods generally alternate between two steps, where the first step is to generate pseudo-labels by either clustering instance features or measuring similarities with exemplar features, and then training the network with target domain data and their pseudo-labels. Pseudo-label-based methods will model relations among target domain instances and achieve state-of-the-art performance to date. Let's review a clustering baseline, which is a preliminary knowledge for the following introduction. First, we need to pre-train the network on the source domain with a classification loss and a triplet loss. This process is almost the same as conventional supervised real-ID tasks. After loading the pre-trained weights, we train the network on the target domain with noisy pseudo-labels, where the classification loss and the triplet loss are also adopted. A strong baseline model for UDA real-ID tasks could be achieved by this two-stage clustering-based pipeline. To achieve optimal performance, we propose a three-stage training pipeline. In the first step, a structured domain adaptation framework is trained to translate source domain images to the target domain. In step 2, the source to target images translated by the structured domain adaptation framework serve as training samples to pre-train the network with ground truth identities. The network can then be roughly adapted to the target domain. In step 3, the pre-trained network is further fine-tuned on the target domain with an improved mutual mean teaching framework, or MMT plus in short. Note that both labeled source domain images and unlabeled target domain images are used for training. To conclude, we introduce a training pipeline with both structured domain adaptation framework and mutual mean teaching framework. Such a joint pipeline can properly make use of both the domain translation-based and pseudo-label-based methods, which are complementary to each other. Let's look into more details. Domain translation is crucial in the synthetic to real adaptation task since the gaps between source and target domains are significant. Directly pre-training the network with raw source domain data could only achieve limited performance on the target domain, which will result in inaccurate pseudo-labels. Here, we introduce to adopt structured domain adaptation, or SDA in short, for domain translation, which was firstly introduced in one of our archive papers. VisDA adopts cycle-GAN architecture as the backbone and introduces an online relation consistency regularization to maintain the intersample relations. Specifically, the intersample relations in VisDA are measured online by source domain and target domain encoders, where the encoders are trained by the clustering baseline as described before. Here are the translated images by officially provided SPGAN and our SDA. After carefully translating the source domain images to the target domain, we can pre-train the network with translated images and their identities under the supervision of a classification loss and a triplet loss. Here are some useful training tricks. First, using auto-augmentation could avoid overfitting on the source domain and improve the performance on the target domain. Second, the GEM pooling layer is stronger than the general average pooling layer. And last, although the target domain images are not required for pre-training, the performance can be further improved by simply adopting unlabeled target domain images for forward operation only. After pre-training with translated images, the network can roughly capture the target domain distribution. For the last step, we fine-tune the network on the target domain with mutual mean teaching framework, which was published in ECCVW 2020. The mutual mean teaching framework adopts a couple of networks, and each network's mean teacher network supervises the training of the other one by predicting robust soft labels. The original mutual mean teaching framework is only trained with target domain data and generated pseudo-labels. However, we argue that properly modeling the intersample relations across two domains is critical to the final performance. So we introduced an improved mutual mean teaching framework, namely MMT+, by jointly training with two domains raw images. We also minimize the domain gaps in mini batches with domain-specific batch normalization layers. In the experiments, we found that the pseudo-labels are much noisy due to the noisy distribution of identities in the target domain. In order to further mitigate the effects caused by pseudo-label noise, we propose to adopt a MoCo loss to maintain the instance discrimination. Specifically, the MoCo loss needs a queue to cache the features encoded by the moment encoder, which is almost the same as our mean networks. So we save the features encoded by our mean networks in the queue, and such features act as negative samples in the MoCo loss. Due to the coupled network in MMT framework, we need two queues to serve individually for each network. Here are the formulations of training objectives. We adopt a hard label loss, a soft label loss, and a MoCo loss for training. At the training stage of MMT+, we also provide some useful training tricks. Firstly, adopting arc phase or cosine phase matrix to replace conventional hard label classification loss could help. Secondly, triplet loss may be redundant as arc phase or cosine phase itself is strong enough for training. Thirdly, as mentioned before, GEM pooling performs better than average pooling. Fourthly, the auto-augmentation should only be used in the previous pre-training stage instead of this stage. Last, resetting the optimizers once upon reclustering could help convergence. Before, we have introduced our training pipeline, and for the inference, we adopt three post-processing techniques. First, we ensemble features encoded by different backbones. Then, we try to eliminate the background interference by subtracting the camera similarities from the person similarities. Last, K-reciprocal re-ranking is adopted on the final similarity matrix. Here are some results for the ablation studies. First, we try to verify the effectiveness of SDA framework. So we compare the pre-training performance of raw images translated by SPGAN, and images translated by SDA. We find that translated images perform much better than raw images, and the images translated by SDA show better performance than those by SPGAN, which verifies that domain translation are crucial to the pre-training performance. Also, we conduct ablation studies on the introduced MMT+. MMT Plus achieved about 3% improvements in terms of mean average precision over the original MMT. As introduced before, we adopt 4 backbones for ensembling, and here are the results by different backbones. To conclude, we introduce a joint training pipeline which takes advantage of both domain translation-based and pseudo-label-based methods. These two kinds of methods are complementary to each other. We also improved the mutual mean teaching framework by modeling cross-domain relations and further mitigating the effects caused by noisy pseudolabels with a Mocha loss. Our method achieved top 3 performance in Visual Domain Adaptation Challenge. Thank you for listening. The code and the trained models are all available, and you are welcome to ask any questions.